Hello, it's Stat 135, Lecture 37. So after a long break, we're back and we are in the last week of classes. On Monday, today we're going to finish regression. On Wednesday, we're going to start Bayesian statistics, and you're going to take quiz 4. And on Friday, hopefully we'll finish Bayesian statistics. I'll pass out a final review sheet and a practice final on Friday, and in our art week we're going to review. So let's take a look at an overview of multiple linear regression. So we have the standard statistical model. Y is x beta plus e, and so this is a linear model. And we'll do today an application of a way that this could arise in sort of a real-world problem. So we have y, a vector of our response variable. E is our error terms. X is a design matrix. And beta is our Tyche Tyche constants. And assumptions in our model is that the xij's are fixed numbers. Our error terms are IID random variables with expectation 0 and variance sigma squared. The EIs are homoscedastic, meaning that they don't depend on x. And we're also going to assume that the EI are normal, although that's not actually part of the standard statistical model. So sometimes we know that beta 0 is 0, in which case x doesn't have that first column of ones. So beta hat, as we know, is x transpose x inverse x transpose y. Beta hat is an unbiased estimator of our beta vector, and the variance of beta hat, so this is a matrix, and sigma squared, however, is not known, so we can approximate that by the residual sum of squares over n minus k minus 1. In the case where beta is 0, it's actually n minus k. So so the residual sum of squares is y minus y hat transpose times y minus y hat. And we have some other sum of squares, the model sum of squares, which is y hat minus y bar transpose y hat minus y bar, and the total sum of squares, which is y minus y bar transpose y minus y bar. And you can see all these, you can see the total, the residual, and the model distances in this picture on the right here. It's obvious that the total is the residual plus model, but in fact the sum of squares of total is the sum of the residual sum of squares plus the model sum of squares. So that if we divide all of these by sigma squared, we get chi-squares with these shown degrees of freedom. And the residual sum of squares and the model sum of squares are independent. So we define a coefficient of determination, r squared. This is close to 1 when our model fits the data well. And in other words, when the data fits the model well, the RSS is close to 0, so MSS is 1 minus RSS. Sorry, that's not right. I meant to say that MSS over TSS is 1 minus RSS over TSS. So when RSS goes to 0, R squared goes to 1. So we define the F statistic as a ratio of two independent chi-squares divided by their degrees of freedom. And This can also be written entirely in terms of the coefficient of determination. So the test statistic, so the null is that there's no relation. So the null for f is that there's no relationship between y and any of the x's. Of course, you can test the significance of each of the beta I, each of the beta i's. So we can make a null that the beta i's are 0, and so to make a t-test of that, we're going to need the standard error. So for the beta I hat, so the standard variance of the beta I hat is the II entry in that in this matrix, and it can be shown that this is the expression shown here. Notice the 1 minus Ri squared in the denominator, where Ri squared is the R squared obtained by regressing the Ri on all the other predictors. So if Xi is correlated with the other predictors, this is called multicollinearity, then the Ri squared is close to 1, and the standard error for beta I hat will be large. So what this means then is that our t-statistic will be small, causing you to accept the null that beta I is 0. So we can get in a situation where if we have multicollinearity, that we can get a large f statistic, causing us to reject the null that f is independent of, that y is independent of all the x's, which indicates that y is dependent on the x's, and at the same time get these t-statistics which show that that the betas are 0. So that would be a contradiction, right? And so so you really need to look out for multicollinearity, because they can lead to very misleading results. Notice that when you add more and more predictors, you'll always make your R squared greater, but you increase the chance of multicollinearity happening. So you want to have as many predictors as you can so that R squared is large, but avoiding multicollinearity. So so to give you a little bit of practice, we looked at this multiple linear regression problem. I wanted to give you an application of multiple linear regression different from what you've seen. So this is an example where beta 0 is 0, and so we have two unknown constants, beta 1 and beta 2. Beta 1 is less than beta 2. Both of them are greater than 0, and we need to estimate these. Okay, we make a linear model. Okay, so we're going to write y1, which is our guess of what beta 1 is. So we'll write y1 is beta 1 plus some error, y2 is beta 2 plus some error, and y3 will be beta 2 minus beta 1 plus some error. So, because it says here in the text that y3 is the distance from beta 1 to beta 2. So we can write this out. So let the x's be the coefficients of the beta. And so you can see that X is a 3 by 2 matrix, 1, 0, 0, 1, minus 1, 1. And so going over the solutions here, to A, we have our linear model. We can find explicitly what beta hat is. So you can see that it's 1/3 of 29 over 30, 29, 31. So that's very close to 10, as you would expect. We can find our estimate of sigma squared, which is so beta 0 is 0 here, so sigma squared estimate is RSS over n minus 2, and because k is 2, and we can find out explicitly what RSS is and see that our estimate is just 1/3. So then we can find the standard errors, and this amounts to looking at our variance covariance matrix and picking out the diagonal entries. Then we can find an estimate for the difference, standard error of the difference. So an estimator of that difference is beta 1 hat minus beta 2 hat, which we know is minus 2/3, and so the variance of the difference is the variance of beta 1 hat plus the variance of beta 2 hat, and then there's a covariance term which you can pick out from your variance covariance matrix and see that the standard error is square root of 2 over 9. And then you can do your hypothesis test. So the hypothesis is that beta 1 minus beta 2 is 0. And so we get a test. So there's n minus 2 degrees of freedom here. And we have n is 3, so this is 1 degree of freedom. And we see that our test statistic is minus 2. It's a two-sided test. So our p-value is the area to the left of minus square root of 2 and to the right of square root of 2, which has area 0.2 according to R. This is greater than 0.05, so we would reject the null, leading us to conclude that in fact, leading us not to reject the null, so we don't reject the null. And so indeed beta 1 and beta 2 are the same. Great, so we are done with regression, and we will start Bayesian statistics next time. Bye-bye.